Hello. So welcome to this event. This is an event we've called Quantum Queries and Astronomical Questions. So I'm joined here by Dr. Phil Sutton, who's going to talk about astrophysics. My name is Dr. Matt Booth. I'm going to talk about quantum physics. And we're also joined by Elizabeth Holland, who's a second-year physics student. And it was Elizabeth's idea to do this event, and she's helped organize this event. So I just wanted to say thank you to Elizabeth before we begin. So what we're going to do, we've got about 15 minutes talk from Phil, 10 to 15 minutes, and then we'll have time for some questions. So Elizabeth will look at the YouTube chat to see if there's any questions typed during the event. And then once we've done that, I'll talk for 10, 15 minutes about quantum mechanics. And again, Elizabeth's job is to keep track of the YouTube chat. And if there are any questions, maybe she'll have some questions. Okay, so without further ado, Phil, did you want to share your slides and begin? I'll remove myself.
I can do. So let me share my screen.
Okay, so thank you.
Okay, so hopefully you can see my slides there. So yeah, as Matt said, I just kind of want to give a 10-15 minute talk around some of interesting questions in astronomy, questions that you may think you know the answer to, but actually there's an alternative answer to them, or they're not as simple as you think. So the first one really is, how many moons does the Earth have? Well, we're quite familiar with our main one. We see it in the sky all the time. And there's an image kind of the what we classify as the dark side of the moon. That's the back edge, the edge that we can't really see from Earth. But it's not the only one. So we can temporarily capture moons. So if you look at the green arrow on Earth here, so the Earth is rotating in one direction. So it's rotating in a set direction. So it gives our night and day. But you notice that we've got this odd-shaped moon asteroid which has its orbit, which is yellow, and it's got arrows which are showing it going in the opposite direction. Now, normally, if a moon has formed with a planet, it would orbit in the same plane as the orbital or the rotation as the planet. So you have to conserve things like the angular momentum and angular energy. But if they form together, they would typically be going the same direction. But you can capture an object. If it gets too close, it can get captured by the gravitational field of the larger object, and it ends up on this bit of a peculiar orbit. And this is what can happen with captured objects. So we do have one. We actually have a few. So this is a temporarily captured one, and this is a simulation to show the orbit as it was captured. So this is the purple object, which is a small object, and it's called 2020 CD3. And you're probably thinking, well, why on earth is it called that? Can't we give it a cool name? Well, when they first discovered these minor planets or minor objects, the first is the year it was discovered, and the letters will denote kind of the month, and then the numbers is the number in that month. So you have this fairly boring catalog name when we discover one of these objects. But the point is, this was kind of discovered in 2020. It came close to Earth. I think the yellow orbit you have here is the moon, and in the center you've got the Earth. So it's come by, and it's been captured gravitationally by the Earth, and it's put it on this really weird orbit. So this is a new moon, and we don't know how long it's going to last, but it's probably going to be temporarily part of our system, and then it will leave and go do something else. And this is a fairly common thing, actually. So these minor objects can get close, they can get captured by the bigger planet, and then you have a new object. So captured objects is one way. And just to give you a bit of an example of that, really, Neptune's largest moon, Triton, is a captured moon. So Triton is actually bigger than Pluto. It has its own atmosphere, and in its own right would have been a minor planet or even a planet. So it's a fairly large object. It's, again, bigger than Pluto, but look at its orbit. So we've got Neptune in the center there, and then we've got all the other orbits here of other moons. They're mostly prograde. So prograde means they're orbiting the same way as the planet is rotating. So they've likely formed together. But you've got Triton here, which orbits in the opposite way. So this is a fairly large object with an atmosphere going the wrong way. You've also another one in here, which is not going to end nicely because it's in between the prograde ones. It's orbiting the opposite direction, and these things can collide. But the point is, capture of these objects is possible. We have captured objects around our own planet. They're not big objects for us because the Earth's quite small, but Neptune's quite large. So Triton, it's possible to have a fairly large object there. So that's one scenario of having another moon, and we have a few of these. Another one, which is one you might not have heard of, is co-orbital moons, or we sometimes call them Trojan moons or Trojan objects. Now, it's quite likely you won't come across the Lagrange points, but if we take a look at the orbit, so you've got the Earth in the center here, you've then got the moon, and the moon orbits around on this yellow line here. So that's the orbit of the moon around. Now, if you looked at the Earth and the moon and you move the camera with it, so it's in that reference frame, there's 5 locations around those 2 objects where you can place an object and it will remain there without any additional forces. So it's where the gravitation and the dynamical forces, or they basically even out, and you can place objects there and they're happy just existing without additional energy, which is good for things like spacecraft. So we can put objects there and we don't need additional fuel because they will just orbit where they are. So they can be stable, but the L1, L2, and L3 are not that stable. So if they move off the point, they'll go on a different orbit. But L4 and L5 at the bottom, they are in front and behind the orbit of the moon by 60 degrees. And it's recently been discovered that we've got objects orbiting there as well. So these are large clouds of dust, small particles basically, that are inhabiting these regions. So we've got one in front and behind our larger moon that we're quite aware of, but we have smaller objects in these locations here, which are technically moons. They have a very odd orbit because they do orbit the same as the moon, but they will move around the point as well. So as they're going around, they actually create spiral shapes. They're very, very unusual orbits, and we have them with the Earth, but it's not just confined to the Earth. So actually, Saturn is probably the best example of this kind of setup. So we have one of the larger moons, Thetis, here, which is classified as Moon 1 in the picture. We then have Callisto and Calypso, which is, so Callisto is the leading Trojan moon, and Calypso is the trailing one. So you've basically got these 3 moons all orbiting together, one in front and behind. And this is a very good example of these Trojan moons, but they exist, in quite a wide range of situations. So Jupiter has Trojan asteroids. So if you have the orbit of Jupiter, so Jupiter was actually where Moon 1 was, and Saturn would be the Sun. There are large collections, 60 degrees in front and 60 degrees behind, that have thousands and thousands of asteroids. So it actually creates these groups in an orbit with Jupiter. So these are quite widespread throughout the solar system. And they look unusual, but they are classified as moons. And we do have examples with Earth. And actually, we have a few examples, not just the clouds, but we have examples that are sharing an orbit with Earth. And one of the scenarios that supposedly formed the Earth-Moon system was a minor planet located at the L4 or L5 Lagrange point, which then somehow came a little bit too far away from the point, and there was a slow collision with the two. There was originally a scenario that formed the Earth-Moon system was from these. So that was the first unusual question or answer with regards to astronomy, and it was to do with the moons. And then I just want to finish on one that you probably realized, but not realized why. So if you look into the sky, you will notice you'll never see a green star. So there's a whole range of different colors of stars. Most colors you'll come across. There's some nice images here of clusters. So you've got an open cluster here, and you've got some nice bright blue stars, some yellow orange stars, white stars. Same again over here. You've got a globular cluster, which is an old structure really. Lots of old red stars. You've got blue stars there, white stars, no green stars. So why are we not really seeing any of these green stars? Well, technically they are there. It's not like they don't exist. It's more to do with our eyes. It's a visual problem for humans in the way that we perceive the visible light coming to us, which is why we see blue, red, white, all the other colours. So if we look at the sun, and Matt will probably mention more about black body radiation in his talk, it overlaps a little bit. But if we look at black body emission from an object, most stars can be treated as emitting like a black body. And so their spectrum they emit, so the relative intensity of the light they emit at a certain wavelength, relates to their temperature. So the cooler the star, their spectrum is shifted more towards the red parts. They peak more in the red, which is why your red giants and that they're fairly cool stars. They also look red to us. And then your bright blue stars, very hot surface temperatures, they're peaking more towards the blue. But the sun, the peak of the spectrum is pretty much in the middle of the visible part of the spectrum, which is about green. But because we're getting equal amounts of blue and red light coming into our eyes, we perceive that as white. So it's not necessarily that there's no green stars around. It's more to do with how we actually see it. So it's a human problem as opposed to an astronomy problem. But if you haven't noticed this before, go out and look at the sky next time you can and have a look at all the different colors, because you can see them visually, just naked eye, really, just looking in the sky. You don't need a telescope. You can see all those range of different colors. But again, you'll never see a green one. There are some situations where they can be almost like an optical illusion. So if you have a certain color star in like next to another color star visually, they can cause a bit of an optical illusion, but they're not actually green. We don't really see them as green. So that was where I just wanted to leave it. Yeah, thank you for listening. If you have any questions, then just pop them in the chat room and we'll see if we can answer them for you. So thank you.
Thank you very much, Phil. That was very interesting. I don't know, Elizabeth, any questions for the chat or questions you want to ask Elizabeth, or should we wait to the end?
I think we'll wait till the end because we haven't got any comments yet. But yeah.
Okay. Yeah. Well, people might be watching this actually not live and maybe watching it later, right? So if you are watching this like after the whatever the date today is, the 17th. So if you're watching this in the future, hello from the past. And you can type your questions in the comments on YouTube, and we'll check it periodically, and we'll try and answer the questions later. So thank you very much, Phil. So now it's my turn, and I'm going to talk about quantum physics, which is very interesting. So I'll hide Elizabeth and Phil. I'll share my screen, and we'll start. So just give me one moment. So it's going to go to one of these infinity patterns for a second until I do this and start playing. Okay, so I have some quantum queries that I wanted to talk about. So there's, if you're not familiar with quantum physics, then this will be very interesting. If you are familiar with quantum physics, and you may have heard some of these things I'll talk about, but I will try and kind of explain in a bit more detail what these things are in terms of kind of wave function. I'll talk about wave particle duality and superposition as well. So my first question then is, what is wave particle duality? So I'll start just by going through the history of the human kind of understanding of light. And we start off back in the times of Newton, where they used to, or at least one leading theory was that light was made up of particles. So this was called the corpuscular theory of light. And this basically came from our understanding of reflection. So I've got a picture of the Taj Mahal here. And if we flip that upside down, it looks almost exactly the same. Okay, so we see reflections all around us in everyday life, and we have a good understanding of how, for example, a tennis ball bounces off a wall. We know that the angle of incidence is equal to the angle of reflection. Okay, so this made people think that light consisted of particles hundreds and hundreds of years ago. But then waves came along. So there's some phenomenon phenomena to do with light that couldn't be explained by treating light as particles. And for example, this effect here, where if you have a shadow of some circular object, then it turns out that the brightest point of the shadow is in the middle. This is called a Fresnel spot, after the French mathematician Fresnel. Some people call it the Arago spot, after an Italian, but things in physics tend to have different names depending on where you live. But this is a phenomenon that can only be explained by treating light as a wave. And if you want to look more about this, there's a nice video from Veritasium about this exact phenomenon. So this is a really nice video. It's not very long. It's definitely worth watching. So the point is, though, throughout history, the kind of fashion, if you like, has changed from treating light as particles to waves. And it seems for different problems, we have to take a different approach. So this idea of wave-particle duality, or the competition between wave picture and light and the particle picture, at least for light, is very, very old. In the 18th century, Maxwell's equations, which are a way to kind of describe light in terms of electric fields and magnetic fields. So, by the way, this is the kind of physics you would learn at university. This kind of cemented the wave picture of light. This is seen as the pinnacle of science in the 18th century, 19th century. So this, when Maxwell wrote down these equations, that was almost like the end of the story. Like light was made from waves. But then, in the 20th century, or at least in the late 19th century, going into the 20th century, there were two big problems in physics. The first one was black body radiation. So Phil mentioned black body radiation, and basically the idea is that the color something emits depends on its temperature. So you see here, there's a nice picture of a fire. You can see some parts are yellow, some parts are red, and even at the top left, there's some parts that are blue. And this is because these different parts are at different temperatures. So temperature, the color of an object depends on its temperature. And this, you've seen this kind of similar plot in Phil's talk. But what I'm showing that Phil didn't have is the difference between the modern theory, which are these colored curves, and the old classical theory. Okay, the old classical theory really didn't predict very well what we would see. It didn't work. But it wasn't until Max Planck came along and said, what if light is composed of small little packets of energy? So small little parcels or particles of energy. So we kind of came back to this particle picture of light. And it works. Planck could recreate these actual experimental curves using a new theory that treated light as particles. So we treated energy as coming in small units of energy. And this is where the name quantum comes from, a fixed quantity of energy. So Einstein kind of took this idea, what he thought was a good idea, and he applied it to a different problem. So the second problem with physics at the turn of the 20th century was the photoelectric effect. So I don't have much time to talk about this, but the basic idea is we shine light from this torch up top onto some metal plate, and in some circumstances that light causes electrons to be emitted by that plate on the left, which is labeled U, and travel towards this plate on the right, which is labeled E. And if that happens, that completes the circuit and the light bulb will turn on. So what we see is that if we use red light, then that doesn't happen. Even if we make the light very intense, we still don't turn the light bulb. If we increase or change the color of the light to yellow, then we get the same effect. Nothing happens. And even for green, sometimes nothing happens. But when we get to a certain color, for example, blue, then the light bulb will turn on. So what this tells us is that there's some property of light that depends on the color and not the intensity. So this could be explained by a particle picture of light. So if each little particle of light has a certain amount of energy, then that has enough energy to affect this metal plate and, as I kind of described, to turn on the light bulb. But if the individual particles of light don't have that energy, then no matter how many of them you shine at the metal plate, then you don't get this current. Okay, so it's the energy of the individual particles that matters in some circumstances, not the total energy or the total number of particles or the intensity. Okay, so that's the photoelectric effect, and that was also explained by treating light as particles. So that is what wave-particle duality is. It's this idea that light has some wave effects and some particle effects. But then in science, we like, especially in physics, we like this idea of symmetry. And then Louis de Broglie came along. So this is how you say this word. De Broglie came along and said the opposite. So if light, which we thought was a wave, can behave like a particle, can particles, such as electrons or protons, can they therefore behave like waves? And he posited that this could be true. And indeed, it turns out that it is. So for a particle, we can associate some wavelength with that particle that depends on its momentum. So particles with lots of energy have long wavelengths, sorry, short wavelengths, and particles with small energy or small momentum have long wavelengths. So we can really talk about the wavelength of a particle. So you may have seen this before. This is the double slit experiment. So this thing here is what we call an electron gun. We heat some metal wire and that emits electrons, and we fire them at some double slit. Okay, and the question is, what do we see on the other side? Well, if we think of the particles or electrons as little tennis balls, okay, and we kind of bat them towards this double slit, we'd expect only the ones that kind of go through the slit to go straight through the slits, and we'd maybe see kind of this double peak pattern, right? One peak from the top slit and one peak from the bottom slit. So this peak really is just like the intensity of light bulb of tennis balls that we see. So this is quite straightforward to understand. This is what we'd expect if particles such as electrons were indeed particles. If we had a torch and we shone light at this double slit, then we know what we get. We get an interference pattern. So the light reaches these slits, and then each of the slits acts as its own new source of light, and then we get spherical waves from each of the two slits, and those waves interfere, and we get interference pattern on the screen. Okay, so this is we do this experiment in first-year physics labs here at Lincoln. This is something you can do in first year and observe this interference pattern. Okay, so what do we see? Well, we actually see that these little particle electrons actually interfere with each other and give this interference pattern when they're passed through the slit, which was very counterintuitive at the time. It was a very surprising result. And you might think maybe it's some statistical property of the electrons. Maybe these electrons really are little tennis balls and they're bouncing off each other. So they do go through one slit, but then after the slits, they kind of bounce off each other and they somehow come up with this pattern. So what people did then was they fired electrons one at a time through this double slit, and we're going to see what they saw. So when they started to do this, it looked kind of random. If you try and see some sort of pattern here, maybe you can trick yourself to thinking you can, but this really does look random. But then as they fired more and more of these electrons one at a time through this double slit, they started to see that they got these fringe patterns, this interference pattern. So it seems that even when these electrons go through the slits one at a time, we still get this wave property. So this tells us then that even single particles have this wave-like property. Okay, so that's the first question. What is wave-particle duality? And the idea is that electrons connect as waves and particles, and light connects as waves and particles, depending on the circumstances. So the next question I wanted to ask a bit more quickly is, what is the wave function? So you may have heard of this idea of a wave function. So what is that? So in classical mechanics, we treat the position of a particle as a definite quantity. So we have some axis. So I'm looking at a really simple one-dimensional problem here. We specify some origin, and we can talk about the precise position of this particle using some coordinate x. And we can use Newton's law, which hopefully you've seen before, to predict what happens to this particle given some applied force. It's going to move around. And in quantum mechanics, we take a very different approach. So we define something called the wave function. It's given this Greek letter psi. It's just a Greek letter. This is some function that describes the position of this particle. But the point is, instead of having some definite points, we have some distribution of possible positions. Okay, so we don't know exactly where the particle is. We just have some distribution, some function that takes some shape. So what is a wave function? Well, let's first ask, what is a function? So a function is some mathematical object that takes in some input. So we input some variable x, we turn this machine, and we output some variable y. So the function would be written y equals the function of x. We input x and we output y. So what is a wave function? Well, it's a function, except the input here is a position, and the output is some number c. Okay, and this number c is a probability amplitude. So we have a wave function, we put in some position, and the output of that function is some probability amplitude. And if we square this probability amplitude, that tells us the probability of finding some particle at that position. So here we have position x1 at the middle of this peak. This c1 that corresponds to x1 is going to be quite large. It's the square of this output of this function. If we took x1 to be kind of towards 0, where this curve is quite low, then c would be quite low, and the probability of finding the particle would be quite low. So instead of using Newton's law to predict exactly what happens to a particle, we use the Schrödinger equation, which I know looks very complicated, and you'll learn about this at university if you do physics. But what we use this to do is to look how the wave function changes over time. And this tells us how the probabilities change over time. So quantum mechanics is inherently probabilistic, and we describe these probabilities using a wave function. So the last question I wanted to answer in a couple of minutes, hopefully, is what is a superposition? So you may have heard people say something like, quantum mechanics tells us that things can be in two places at once, which kind of sounds strange. So what exactly do they mean when they say this? So we'll consider an example of a classical coin versus a quantum coin. So imagine we have a coin that could be heads or tails, okay? And classical physics tells us that if I flip this coin and it lands on the table and I cover it up, then that coin could only possibly be heads or tails, okay? So even if before we look, we know for certain that it's either heads or tails. Now, the slight subtle difference for quantum physics is that we put emphasis on measurement rather than existence. So in quantum physics, the coin can only be measured as heads or tails. So when I move my hand and look at the coin, then it's going to be heads or tails. But before I look at the coin, so before I flip it, it lands on the table and I cover it up, before I look to see what it is, we would describe the coin mathematically as being in a superposition. So what does this mean? A superposition is a sum of all the possibilities times these amplitudes that we saw when we looked at the wave function. So for a fair coin, the probabilities would be 50-50, right? So for the wave function to be a superposition of heads and tails, it looks like this. So the wave function is this psi, and this is equal to some amplitude c times heads plus some amplitude c for the tails times tails. So in this kind of description, the probability of seeing heads when I move my hand is the square of the amplitude for the heads. And the probability of seeing tails when I move my hand is the square of the amplitude for this second part, for the tails part. So you may have heard of this in terms of Schrödinger's famous thought experiment, where a cat can be either alive or dead. So there's some cat in the box with some radioactive material, but you don't know if the radioactive material has kind of radiated or not. So before you look, the cat is in some superposition of alive and dead. Okay, so the probabilities work in the same way. It's the square of these amplitudes c. Tells us the likelihood of the cat being alive and the likelihood of the cat being dead. So I just wanted to end by saying that this probably sounds very weird, the fact that two things can be, we can't say exactly whether something's true or false. It can be in some weird mathematical combination of the two. But I think this may sound weird to us because of our kind of Western logical tradition is binary. So in our whole civilization is, at least Western civilization, is nowadays grounded in digital technology, right? Where we have Boolean logic. 1 is true, 0 is false. In logic, we'd write that as A or not A. And this is all we have for logic, okay? But there's some ancient logical traditions, such as a Buddhist logical tradition called CATUSKOTI, reminds us of Schrodinger's cat. And they have 4 possibilities. They have A is true, A is false, but they also have the logical possibility that A is true and false, and A is neither true nor false. Okay, so don't worry about these things on the left, look on the right. So they have these 4 possibilities: true, false, true and false, or neither true nor false. Okay, so to a Buddhist who's kind of thinks about the world in this logic of the CATUSKOTI, maybe the superposition wouldn't actually be that weird. So I just wanted to finish by showing you all the possible interpretations of quantum mechanics. Okay, so the thing, when I think of questions about quantum mechanics, a lot of them don't really have definite answers, because the philosophical interpretation of quantum mechanics is still very much an open question, and all those interpretations are experimentally indistinguishable. Okay, so thank you very much, and hopefully we have some questions now. If not, that's fine. We can finish there. But let me bring back Phil and Elizabeth. So I think I went over a little bit there, as I kind of knew I would. I tried to finish them.
Pretty close.
Were there any questions from the chat, or questions you had, Elizabeth?
Me? What interpretation would you go with if you had to choose one?
Ooh.
Like your favourite?
So
I'm hoping there's many worlds.
the one, no, actually it's not. So the one we teach at university traditionally is the Copenhagen interpretation, which just has some sort of collapse. So we treat measurement as a very special thing. The act of measurement collapses the wave function into one of these possibilities. So we have some wave function that could be in a superposition of dead or alive, or heads or tails, and we measure it. I remove my hand off the coin and we measure it, and then suddenly, out of nowhere, by magic, one of these possibilities manifests as reality. And this, we kind of have some technical way of describing that. That's the Copenhagen interpretation. That's what we teach. I'm starting to come around to one called the pilot wave interpretation. So we've recently had a member of staff start at Lincoln who's an expert in so-called Bohmian mechanics, pilot wave interpretation, and he's slowly convincing me that that could be the case. And I don't like many worlds theory. This is many worlds theory is that when you measure a superposition, then the universe splits into 2, where one of the possibilities happens in one universe and the other possibility happens in the other universe. Okay, I don't like that, because I think you have to have a much better reason to invoke a completely new universe. We have no evidence for that, so I think it's towards the bottom of my list. But you said you hoped I would say that one. So is that the one?
I hoped you wouldn't for that reason. I agree with you.
So I think it's a nice idea, but I think I don't know. I would need a lot more evidence other than that it's just plausible. So it's plausible, it's possible, but I don't know. It's a bit of a stretch to my mind anyway. But who knows, right? I think by definition we would never know. So I don't know.
Well, so
Any other questions? Go on, Phil. Sorry.
I was just going to say, are these things untestable? Because if they're untestable, you can't really hold them to much, can you?
Yeah,
you have to be so careful.
Yeah. So because the Copenhagen interpretation is the one that we traditionally teach in universities, that's kind of the default language. But there's other interpretations that are equally valid. So we do have to be careful not to speak as if we're for certain the interpretation in terms of metaphysics, because we don't really. Yeah,
and I suspect it basically crosses over into some of the weirder questions in astronomy, in that, well, multiple universes is the same sort of thing. You can have a universe inside a black hole. It's endless, but you can never really test them. So at what point are they actually useful to talk about?
Yeah. Well, yeah. I mean, they're useful to talk about for sure, but I think, like you said, we have to be careful not to be too overly certain and pretend that we know things that we don't actually know. So, what's your thoughts on the many worlds interpretation? Like, imagine if you had an infinite number of universes to look at planets.
But it just makes it more complicated. I mean, we're not capable of looking at the whole what we've got at the moment. I mean, I don't know if this is probably just to let people know how we do astronomical observations and research is that we don't go out to an observatory anymore, sit on a mountaintop and fiddle with a computer and move it around, take pictures. We don't do that. That's not what astronomers do. What we do is we set it all up robotically, and it just scans the sky. Then we go back a few years later to look at the actual images and historical data sets. There's too much data that we can't actually go through. So if we had more universes, well, yeah, it'd be difficult to even comprehend the kind of information we'd get if we could even look at them. I think that, like you said, they're nice ideas to think about because it offers some really interesting ideas. But when you actually want to figure out if they're right or wrong, you hit some fairly significant problems.
Yeah.
So yeah, I mean, I prefer observations, obviously.
We do take students to observatories, though, right? Usually we go to La Palma, I think. But
yeah,
this year,
so actually we do visit them. So, I mean, when I was doing my PhD, I still got to use one of the observatories at La Palma in remote control, I'd like to add. But so the point is,
a big handle and,
no, we don't do any of that. So you basically, you can get trained how to use them because modern astronomers don't necessarily have the contact with them, so they don't really know how to use them, or they're not familiar with observations, but it's key to know to do your research. So you can get access to them for like training and stuff, but most of the time, most professional astronomers are either writing computer simulations, looking at data. They're not really going to exotic locations like you may think in the movies. There's a handful of us that do, but not many.
Anything else, Elizabeth, you can think of?
I never ever really understood what actually causes the wave function to collapse in the first place by observing something, if that makes sense.
So again, this is one interpretation, and there's several explanations about that part of that interpretation. Yeah. So, one idea is that when you make a measurement, so a lot of people, when they hear the word measurement, they think that we're talking about like somebody who's conscious, right, and looking at it. When we say measurement, you can really think interaction. So when you measure something, you're necessarily interacting with the system. In order to measure something, you have to interact with the system. Okay, and then you kind of couple your interaction, your measurement device with the system itself, and it becomes one system. Okay, and it's kind of entangled with the system, and then this causes, yeah, it's difficult to explain on a YouTube chat. But there's this idea of decoherence, which is one of the things I put on the list there. But we can chat about this in more detail another time. Yeah. But that's one. This is kind of another way to think about quantum mechanics. The difference between quantum mechanics and classical mechanics is that in quantum mechanics, the system being measured and the measurement apparatus cannot be described separately. They're part of the same system. In classical physics, you think about some system, and we tend to think about like passive movements, where we can measure the state of the system without actually affecting the state of the system. But in quantum mechanics, we just can't do that. When we measure, we interact, and that affects the system. So this is kind of connecting between the system being measured and the measurement apparatus itself. So quantum mechanics is all about measurement. Some interpretation of quantum mechanics, the whole kind of notion of reality is measurement itself. So measurement is what creates reality, right? So I don't know if that answers the question.
Yeah.
But I'm sure we'll discuss this at another time. Okay, so I think we can stop there. We've gone over time anyway already. So okay, so I want to say thanks to Phil for the talk, and thanks again to Elizabeth. So for Elizabeth to come up with this idea and help arrange it whilst doing lectures and stuff, it's really nice. So thank you, Elizabeth. I hope you enjoyed it.
Thank you.
Got something from it. So we'll stop there. So everyone watching, have a good day, and we hope to see you soon on some of our other outreach talks. Okay, thank you. Bye.
Bye.